In practice, the theoretical cycle proved to be unworkable. So, to make it work efficiently, it's necessary to modify the times when the valves open and close and when ignition occurs. In other words, to change the valve and ignition timing. The animation which follows uses a practical timing diagram like this to illustrate changes that have had to be incorporated into Otto's theoretical four-stroke cycle in order that it could work more efficiently. The timings shown are imaginary and are not to be associated with any particular type of engine. The first change to notice is that the inlet valve has been arranged to open 20 degrees before the crankshaft reaches top dead center. This will ensure that the valve is fully open early in the induction stroke. This means that there will be no delay between the piston moving down and the mixture flowing into the cylinder, as would normally occur because of the inertia of the mixture. The incoming mixture can therefore keep up with the descending piston more easily. The momentum of the mixture increases as the induction stroke proceeds, and towards the end of the stroke it is such that the gases will continue to flow into the cylinder even though the crankshaft has passed bottom dead center and has driven the piston upwards slightly. Closure of the inlet valve is therefore delayed until after bottom dead center, when the gas pressure inside the cylinder approximately equals the gas pressure in the induction manifold. As the piston continues to move upwards, the inlet valve closes and the gas is compressed. By squeezing the gas into a smaller space, the pressure that it will exert when it's burnt is proportionally increased. It should be noted that as the gas is compressed, it becomes heated adiabatically, in the same way that a bicycle pump warms up in action, as well as by conduction from its hot surroundings, and the pressure consequently rises to a higher value than that to be expected from the reduction in volume alone. Before the piston reaches the end of the compression stroke, in this particular case 34 degrees before the crankshaft reaches top dead center, the gas is ignited by a spark. The momentum of the moving parts carries the crankshaft up to and past top dead center, whilst the flame is spreading through the combustion chamber. The intense heat raises the pressure rapidly to a peak value which is only reached when combustion is complete. The ignition point is arranged so that complete combustion, and thus peak pressure, coincides with the crankshaft being at about 10 degrees past top dead center, which means that the piston is a short distance down the cylinder on the power stroke, an ideal position from where to take maximum mechanical advantage in driving the crankshaft. If the exhaust valve were not opened until bottom dead center, the pressure of the gases remaining in the cylinder would resist the upward movement of the piston on the exhaust stroke. However, as the piston descends on the power stroke, the pressure within the cylinder falls rapidly. By the time the crankshaft has turned through 45 degrees after top dead center on the power stroke, the pressure in the cylinder has dropped to approximately half its peak value. And by 90 degrees of crankshaft rotation after top dead center, most of the pressure energy in the gases has been converted into mechanical energy. If the exhaust valve is opened before the crankshaft reaches bottom dead center, shown here in our example at 62 degrees before bottom dead center, the residual pressure will start the first stage of exhaust scavenging, so that by bottom dead center there is very little residual pressure on the piston, which will impede its progress when it starts the exhaust stroke. This procedure is called pressure scavenging. It does not produce a significant loss of mechanical energy for two reasons. Firstly, there's only a short distance left for downward movement of the piston after the exhaust valve is opened. And secondly, relatively little pressure is still being exerted on the piston by the cooled and expanded gases. Finally, the piston moves upwards, forcing the remaining gases out of the cylinder. In our example, the exhaust valve is left open until 30 degrees after the crankshaft has passed top dead center, to encourage the gases to scavenge the cylinder as completely as possible by their own momentum. We've already mentioned that the exhaust gas must be forced out of the cylinder against the pressure of the atmosphere. This fact becomes very significant when we discuss supercharged and turbocharged engines in a later lesson. As there is little change in the cylinder volume as the crankshaft rotates through the ineffective crank angle, the weight of charge entering into the cylinder and the scavenging of the burnt gases can be improved by opening the valves early and closing them late. These changes to the valve timing are named valve lead, valve lag, and valve overlap. Valve lead refers to when the valve opens before the theoretical opening time. For example, when the inlet valve opens before crankshaft top dead center, or when the exhaust valve opens before crankshaft bottom dead center, as shown here. Valve lag occurs when a valve remains open after the theoretical closing time. For example, when the inlet valve remains open after crankshaft bottom dead center, or when the exhaust valve remains open after crankshaft top dead center. Valve overlap refers to a period when both valves are open together. During this period, the action of the exhaust gases flowing out of the cylinder tend to reduce the gas pressure in the cylinder to below that of the mixture in the induction manifold. Thus, the mixture starts to flow into the area of low pressure and assists in displacing the remaining burnt gases. By doing so, it improves the volumetric efficiency of the engine by inducing a greater weight of charge into the cylinder. The volumetric efficiency of an engine can be found by comparing the weight of mixture induced into the cylinder during engine operation to that which would fill the cylinder under standard atmospheric conditions when the piston is stationary at the bottom of its stroke. It's very important to remember that the valve timing for any particular aircraft engine, the setting which determines when the valves open and close, is fixed and does not vary with engine speed. We've already mentioned that engine efficiency can be improved by opening and closing the inlet and exhaust valves at times other than crankshaft top dead center and bottom dead center. We'll now look a little closer to see more precisely why this procedure works so well. About the crankshaft position of top dead center and bottom dead center, the distance the piston moves is very small compared to the large angular movement of the crankshaft. Compare in this animation the linear distance travelled by each of the two pistons for the same angular movement of the crankshaft. Now, in the left-hand illustration, as the crankshaft moves through an arc of 45 degrees of rotation about crankshaft top dead center, you can see the relatively short distance that the piston travels up and down its stroke. Conversely, at the right-hand side, while the crankshaft still only rotates through an arc of 45 degrees, but this time halfway between top and bottom dead center, the piston travels considerably further. Because of this minimal piston movement as the crankshaft moves around top and bottom dead center, this arc is called the ineffective crank angle. Historically, a device known as an indicator was attached to research and experimental engines. This measured both the variations in cylinder pressure and the changes in piston position throughout the 4 strokes of the operating cycle. By means of a mechanically operated pen, the device plotted pressure against volume on what was known as an indicator diagram, or pressure-volume PV diagram, an example of which is shown here. Modern technology utilizes electronic sensing devices to obtain the same information. The indicator diagram is used to plot the variation in the pressure obtained. This determines the shape and the area enclosed by the graph. This area is representative of the work done on the gas and the power produced by the engine. This picture shows the indicator diagram opened out, so that the pressure areas under the curve can be more easily compared and measured. The area within the power column represents work done on the piston during the power stroke. The blue areas represent work done by the piston in compressing the charge during the compression stroke and exhausting the cylinder against back pressure in the exhaust stroke. Subtracting the sum of the blue coloured areas from the area within the power column leaves us with the red block. This is the average pressure on the piston during the working cycle. It's termed the indicated mean effective pressure, or IMEP.